So this is the second half of the lecture on nuclear chemistry. In this session, we're going to look at nuclear stability as well as half-life. So make sure that you watch part 1 and review those notes before you look at part 2 so that this part will make sense to you. So in the first part, we looked at nuclear equations and writing those nuclear equations for what is happening in the nucleus as the as the nucleus decays through radioactive decay. And in this part, we're going to look at how we know that an atom or a nucleus is radioactive, as well as the time factor. So we'll look at half-life and how long it takes for these different substances to decay. So the first thing I want to draw your attention to is page 915. And on page 915, you have a graph that looks somewhat similar to this. I'm going to draw this very crudely here. So on the bottom, on your x-axis, you have the number of protons. And then on the y-axis, you have your number of neutrons. And you've got this line that kind of runs diagonally up like this. And this line, we call this the line of stability. This is where we have a 1-to-1 ratio between our protons and neutrons. And as an element is closer to this line of stability, sometimes this is referred to as the belt of stability. Let me write that on there too. As long as a nucleus of an atom remains close to this line or on this line, then it can be considered to be stable. Okay? But as we start getting the number of neutrons moving away from the number of protons, so we start out with some of our smaller elements. They're clustered right around this line. But as we start to move up, we start to see nuclei deviating from this line. And so our trend kind of moves in this direction away from this line or away from the belt of stability. And as we move away from this line of stability, that's what makes an atom or a nucleus radioactive. Because at this point, it just isn't strong enough to hold on to all of those neutrons. It doesn't have the attraction, as you learned about in your Edpuzzle video, to be able to hold on to all of those neutrons. There's just not enough pull in the nucleus. So what happens is they start to decay. Okay? And we can look at where these are to determine what type of decay we're looking at. So if we look a little bit closer here, we see kind of a trend, and in your book this is in blue, and so we've got kind of this little trend in blue. It deviates from our line here somewhat, but still kind of goes in a straight pattern. But then we start to get some of these outliers, and so I'll do these in green. We start to get a lot of outliers away from this belt of stability, away from this line of stability, that are sitting way out here where they have a lot of neutrons compared to their protons. And so when we look at where these are, we get some general patterns in how these different atoms are going to decay. And this is on page 915 in your book. So if we have a high neutron to proton ratio, okay, so they're very neutron rich, they can move closer to the belt of stability by emitting a particle. because beta emissions can decrease the number of neutrons and increase the number of protons. So if they have a high neutron to proton ratio, in other words, they are lying above the belt of stability, those green dots that I drew in on the last picture here. If they're above the belt of stability, they tend to decay by beta emission. Okay, that weird B there, that's the Greek letter beta. Okay, and remember that beta emission was essentially getting rid of an electron, and so its atomic notation is like this. So that's if they have a high neutron to proton ratio, they're above the belt of stability. If they have a low neutron to proton ratio, they are below the belt of stability. Oops. Then they are essentially more proton rich. And so they can move closer to the belt of stability through positron emission or electron capture, because both of those increase the number of neutrons while decreasing the number of protons. So they can decay, and again, these are tendencies. This isn't 100% in every case, but they tend to decay by electron capture or positron emission. Remember, electron capture is when they capture one of those beta particles. They capture an electron, and so that shows up on the left side of the equation. And then a positron, remember, is the positive equivalent of an electron. So that's going to show up on the right side of the equation. The other type of radioactive, and keep in mind, these different these different atoms tend to be radioactive. If they're above the belt of stability or they're below the belt of stability, they're going to tend to undergo radioactive decay. So the third circumstance we look at are nuclei with atomic numbers greater than or equal to 84. Okay, and we tend to call those heavy nuclei. Okay, so their atomic number is 84 or greater, which typically means then, Z, of course, is going to be greater than or equal to 84, and A is going to tend to be greater than or equal to 168. Not in every case, but by and large, these are going to have more neutrons than they have protons, so they're going to have a very high A, or a very high mass number as well. These tend to undergo alpha emission, which, remember, is the equivalent of a helium nucleus. This decreases both the number of neutrons and the number of protons by 2, which moves them closer to that belt of stability. Okay. If we look at sample exercise 21.3, on the top of page 916, they ask us to predict the mode of decay of carbon-14 and Xenon-118. So carbon-14, it is element 6, so it has 6 protons, and it will have 8 neutrons. Remember, we looked at this one to begin with. With its mass number of 14, then it's going to have 8 electrons. So this is considered a high proton to neutron ratio because it's above 1. Okay, so carbon-14 would tend to decay by beta emission. Okay. If we look at Xenon-118, what we're looking at here is that its atomic number is greater than or equal to 84. It's 118. And so, oh, sorry, that's not correct. I was looking at its mass number. Hold on. So Xenon 118, okay, so Xenon has an atomic number of 54. Okay, so that's its Z value. And so its A value is 118. So what we need to do is figure out how many neutrons does it have. Okay, well, if we subtract 118 minus 54, we get that this Xenon 118 is going to have 64 neutrons. Okay, so it has 64 neutrons. So it has a higher neutron to proton ratio. It is above 1.0, but it's lower than other atoms of its size on our figure. So if we look back at figure 21.2 and we look at other elements in that area, so if we look at our number of protons, which is 54, and we follow that up, we see really that with 64 neutrons that our Xenon 118 lies above our red line, but below that blue belt of stability. Okay, so this is considered a low proton to neutron ratio. And so our Xenon 118 is going to decay by either positron emission or electron capture. You think, but wait a minute, carbon is so much smaller and it has beta emission. Why is it not the same thing? Well, if we look on our table, 21.2, and we look at those small elements that are down there, carbon-14 has more neutrons than it should. More neutrons than other elements that are like it. So it sits outside of the belt of stability above it. But when we look at Xenon 118, and you think, well, it does have a neutron to proton ratio above 1. That is true. It has 10 more neutrons than it does protons. But when we compare that to other elements that size, it's smaller. So in other words, it has fewer neutrons than we might expect of an element that size. So its proton to neutron ratio is lower than we would expect. And so it's going to decay through either positron emission or electron capture. Okay. Now, the next thing we see as we look on pages 916 and 917 are what we refer to as radioactive decay chains. And this is essentially what the first part of your lab 11 is. We're looking at a radioactive element and we're following it down until it becomes stable. And most of the time, 99% of the time, this isn't going to happen with one chain, with the emission of one particle. For instance, on page 917, you see in figure 21.3, you see a radioactive decay chain for uranium-238. Okay, and this is going to continue until we get all the way down to lead-206, which is considered a stable isotope. So what you see here is that each red arrow indicates beta emission and each blue arrow indicates alpha emission. Okay, so when we write this, we have uranium-238, so that's its mass number, and I know uranium is element 92 on the periodic table. And if I look at that, my first decay as I drop down is alpha emission. So I'm going to have some element that it's going to come into, that it's going to turn into, through alpha emission. So I have to figure out what is my daughter nuclide. Remember, this is our parent nuclide. And I have to figure out what is my daughter nuclide. And I do that through subtraction. So I'm going to say 238 minus 4, that's 234. 92 minus 2 is 90. And I'm going to go to my periodic table, and element 90 is thorium. So in the first step of the radioactive decay of uranium-238, I produce thorium-234. Okay, so that's my first step. That's the first thing that happens. So then, okay, my daughter nuclide, which is thorium-234, becomes my parent nuclide of the next reaction. So I move it over to the left. And I see that now I have a beta emission. And so I've got to figure out, all right, fine, what is my daughter nuclide now? And my daughter nuclide is going to be protactinium-234. Okay, and now this daughter nuclide becomes the parent nuclide of the next reaction. And we're going to follow this all the way down, alternating between alpha and beta decay, because those are our two main types of decay. We're going to alternate between alpha and beta decay until we get all the way down to lead-206. Okay, so our parent nuclide is going to decay, emitting either an alpha particle or a beta particle and a daughter nuclide. That daughter nuclide becomes the parent nuclide of the next reaction. And then we get another daughter nuclide. And that daughter nuclide would become the parent nuclide of the next reaction. So that's what you are looking at in the first part of Lab 1. You're going to look at what particle is emitted, and I have pictures of that in the PowerPoint. And then you will write out your nuclear equation and follow that all the way through all 20 of those steps as we go through. Okay. Now, the one thing we have to talk about with these radioactive decay chains is something that we call the magic number. Okay. And this is looking at how many protons and neutrons something has and whether or not it can be stable. And so our magic numbers are 2, 8, 20, 28, 50, and 82. And these are the number of protons and or the number of neutrons. Okay. They're more stable than those who don't. So, for instance, helium is stable because it has 2 protons and 2 neutrons. Okay. Oxygen. Oxygen-16 is stable because it has 8 protons and 8 neutrons. Okay. The other thing that we have to look at in terms of stability is nuclei with even numbers. Of protons and neutrons or both are more stable. Okay, that's why lead-206, okay, is so stable. First of all, its number of protons is 82 because its atomic number is 82. So it has a magic number of protons, but also its mass number, or its Z, 206, is an even number. Okay. Lead-203, not stable as much. Because it does have the correct number of protons, but its number of neutrons is odd. And so it would not be as stable as lead-206, which has an even number of neutrons. Okay, so that's something to look at when we look at these radioactive decays. Okay. Sometimes, and this is on your cheat sheet on the first page, you see that we can get emission of a neutron or a proton as a nuclear particle. And a lot of times in research, we use these neutrons as the bombarding particles. Okay, for instance, if we look at iron 58, okay, we can bombard that with a neutron to give us iron 59. Well, iron 59, not really stable. Okay, so this iron 59 is going to quickly decay into cobalt 59 by beta emission. And then we can take that cobalt 59, fire a neutron at it, and get us cobalt 60. And cobalt 60 is used in radiation therapy. So that would be for people undergoing cancer. So we can't really create cobalt 60 directly. Okay, we have to start with iron 58 in order to get to cobalt 60. Okay, so we can use neutrons as the bombarding particles. And so when you see that, if it's a bombarding particle, or if your problem says it was bombarded with neutrons, then that means that it has to be on the left side of the equation. We're firing it at the nucleus, so it's going to combine with what's already in the nucleus, so it has to be on the left side of the equation, the essentially the reaction side of the equation. The elements past uranium on the periodic table are called Transuranium Elements, and we have created those through nuclear transmutations. In other words, we have bombarded these the uranium with neutrons in order to produce these other types of atoms and elements. Okay. And new advances in the detection of these decay patterns has allowed us to be able to go all the way up to 118 on the periodic table. Okay, now some of these, they last microseconds. Some of these transuranium elements only last for microseconds until they decay. But they still exist, and we do that because we bombard them with other things. So the last part here that we're going to look at are the rates of radioactive decay. So some, like I just mentioned, of these atoms last microseconds, milliseconds. Okay, some last for millions of years. Okay. And so we can look at their half-life. We can look at how they decay. And so the half-life, you'll hear this term a lot, and this is what your second part of Lab 2 is about. Half-life is the time required for half of any given quantity of a substance to react. So basically, half-life is how long does it take for half of a given substance to react and essentially go away, turn into something else. Okay.
So if we look at an example, we can look at strontium 90. Okay. Strontium 90 has a half-life, and we abbreviate that with a little t with the sub-half here. The half-life of strontium 90 is 28.8 years. So it takes 28.8 years for half of our sample of strontium 90 to decay, to turn into something else. So if we start out with 10 grams of strontium 90, after 28.8 years has gone by, we now have 5.0 grams. And if we go another 28.8 years, we'll have 2.5 grams. And if another 28.8 years, we'll have 1.25 grams. Okay. Now, I want you to keep in mind, this isn't disappearing. It's not disappearing. It is just decaying into something else. Okay. It decays to yttrium 90. So after 28.8 years, half, or 5 grams of my strontium 90 has become yttrium 90. And I'm left with 5 grams of strontium 90 left. And then after another 28.8 years, okay, half of that has become yttrium 90, and I'm left with 2.5 grams of strontium 90. Okay. And so these nuclear decays are not going to be influenced by temperature. Okay, so it doesn't matter what the temperature is. It doesn't matter what the pressure is. It doesn't matter what any of the environmental conditions are. Strontium 90 has a half-life of 28.8 years, and we can't speed that up. So if we look at sample exercise 21.5 on page 921, we see that the half-life of cobalt-60 is equal to 5.27 years. Okay. How much of a 1.000 milligram sample of cobalt-60 is left after 15.81 years? So they want to know how much is left after 15.81 years. So the first thing we have to do is figure out how many half-lives have passed. So I'm going to take my time that they've given me, and I'm going to divide that by my half-life. And I get 3. So 3 half-lives have gone by. Okay. And I started out with a 1.00 gram sample. So when I start, I have 1 gram. Okay. And after 1 half-life, then I'm going to have 0.500 grams. So that's 1 half-life. And then I'm going to go through another half-life. Oops. Okay. And after that second half-life, I'm going to have 0.250 grams. Okay. I'm just dividing by 2 with each step, because remember, half of it is going to decay. So in my first half-life, half of it decayed. I went from 1 to 0.5. And then after my second half-life, I went from 0.5 to 0.250. And then if I go through another half-life, so this will be my third, I have 0.125 grams. So the answer is 0.125 grams of cobalt-60. Sorry about that. My pen went a little crazy on me. It's got a mind of its own today. 0.125 grams of cobalt-60. Goodness. Okay. Now here's where I see students make a mistake on this type of problem. They go, okay, 1.0 gram. 1, they put their 1 here, they put their 2 here, they put their 3 here. Okay, I'm done. But you're not. If you look at just the numbers you've gone through, that's 3 numbers, but it's only 2 half-lives because you have to look at what you start with. Okay, so make sure you carry it out. And I like to write my half-lives on top of my arrow so that I can keep it straight, that I need to go all the way through to 3 half-lives. Okay, another type of problem that we can see with half-lives, and we see this in the practice exercise here, a radioisotope of technetium is useful in medical imaging techniques, and its sample initially contains 80. Oh, it's not wanting to write. We have 80.0 milligrams, okay? And we want to know, so after 24 hours, only 5 milligrams remain. What is the half-life? So we've got to figure out what is our half-life of our technetium. All right. So what we're going to do is we're going to start out with 80 because that's how much we started with, and we're going to take it through a series of half-lives. All right. So after 1 half-life, I'm going to have 40. Okay. If I go through, so that's 1 half-life. So if I go through 2 half-lives, now I have 20. And I'm going to go through another half-life, and now I have 10. And I'll go through another half-life, and now I have 5. Okay, which is how much they told me I had remain. Oops, it's milligrams. I put grams on every one of these. Sorry about that. All right. So I went through 4 half-lives to get to 5 grams. So in 24 hours, we had 4 half-lives. Okay. So now we can say 24 divided by 4 gives me a half-life of 6.0 hours. So my half-life is equal to 6.0 hours. Okay, and we can plug this in and make sure we've got it right. So after 6 hours, I had 40. After another 6 hours, which would equal 12 hours, I have 20. After another 6, which would equal 18, I had 10. And after another 6, which would be 24, I had 5. So I can double check and make sure that I've done that correctly. So my half-life is 6 hours. So when you're given a problem like this and they're asking you, they're telling you how much you started with, and they're telling you how much you ended up with, and they're asking you, what's the half-life? Well, just take it through. Take your amount that they told you started with and take it through your half-lives until you get the amount that they tell you that remains. And you count how many half-lives you had to go through, and then divide your total time by that number, and that will give you your half-life. Okay, so that's how we look at half-life problems. Okay, and so that's how you're going to work those problems. We don't get really much into looking at other equations. The rest of your chapter here, or the next little section of your chapter, gets into calculations based on half-life, where we look at activity rates, and we're not going to get into that for our purposes. Okay, we're just going to look at these basic types of half-life problems. We're also not going to get into the energy
at all, looking at the energy changes that can take place. We're not going to get into that at all. And we're also not going to talk about nuclear fusion. Everything we've talked about so far has been about nuclear fission, which is splitting or breaking apart of the nucleus. Nuclear fission is when you put things together. And so we don't really talk about that very much because really the only place we can really observe this is on the surface of the sun. All right, so that is pretty much the end then of chapter 21. So you have your labs. Okay, lab 11, and I have parts 1 and part 2 of that. Part 2 is about half-life, and you're going to make some graphs on half-life based on the images that I've put for you in your PowerPoint. And then you're going to have some problems that you're going to work that are nuclear equations and half-lives. So if you start working on those and have trouble with those, just make sure you send me an email or a text and I can work with you on those. So this is our last official class meeting. You have labs that you need to get done, and you have those problems you need to get done. Also, your Unit 6 assessment covers just Chapter 21. That's what serves as your final for this class. I sent out emails today to those of you who are missing work. So you need to get on that and get that done. You've got 10 days because those are due on May 7th. Went back a couple months there. Those are due on May 7th. I will not take anything after that point because I have to have time to get it all graded and get your grades submitted. I'll probably be out of pocket a lot next week, so I would encourage you to get started on these assignments this week. That way, if you have any questions, you can ask me while I'm still available. I'm taking a little vacation next week, and I don't know how good my internet service is going to be. So just make sure that you you start working on that early, so you can ask me any questions that you have. So I enjoyed our semester together, guys. I hated that it got cut short by this coronavirus. I hope that we can get back to normal for the fall, and maybe I'll see some of you around this fall. To those of you who are graduating or transferring, good luck to you all. Please keep in touch. I like to keep up with my former students and what they're doing, where they're at. So please keep in touch with me. If you have not already, please fill out your student survey of Instructor. You get to do this for each one of your classes. You should have received an email about this, but please go in and do those student evaluation of Instructor. We really rely on that information to help us improve. So please, 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 if you haven't already done that, go in and complete the evaluation of all of your different instructors for this semester. Bye, guys.